A vector in a three-dimensional space can be represented by an ordered triple of real numbers. These numbers are called the components of the vector. So a vector in 3D has three components. Over here, we can see a bunch of vectors with three components, and these are the vectors in 3 dimensions. Now the question here is to find out for what values of x and y is this vector orthogonal to both this vector and this vector. So this is a three-dimensional vector, and we would like to know that for what values of x and y. So in this vector, you can see we have two components, x and y, and we would like to find out their value under a condition that this vector is orthogonal to this vector, and this vector is also orthogonal to this vector. So what does the orthogonality of two vectors mean? Two vectors are orthogonal when their dot product is 0, which means we have to find values of x and y for which the dot product of this vector with this and the dot product of this vector with this both equal to 0. So basically we want to find the values of x and y under a certain condition, and the condition over here is orthogonality. Okay, now let's try to attack this problem. So if this vector, the first vector that is given, 1, x, y, these are the entries of the vector, is orthogonal, if this is orthogonal to this vector, in the first case, let's say, so this vector has components 3, -1, and 4, then what that implies is that these two vectors, the dot product of these two vectors is equal to 0. So I'm taking the dot product of these two vectors, and that's equal to 0. Now, if the dot product of these two equal to 0, let's perform this dot product operation, which gives us, so how do you take the dot product? You multiply the corresponding components of these two vectors, and finally you add all of them up. That is the idea. So you multiply 3 with 1, that gives you 3, and then you multiply -1 with x, that gives you -x, and then you multiply 4 with y, and you add all of them up, so it's going to be 4y. So this is equal to 0. Okay, so we have found a really nice equation out of this dot product. Now, in the second case, we'd like to take the dot product of this with this vector. So let's do that and see what happens. Now we can write, if the vector, the first vector was 1x, y, this is orthogonal to the last vector that was given with components -4, 1, 2. These are the components of the last vector, if you recall. So we would like to see that their dot product, because they're orthogonal, so their dot product must be equal to 0. So you write x, y, this first vector, and then the last vector, you take the dot product of them, -4, 1, 2, and their dot product has to be 0, which gives, so you take the dot product, so you multiply the corresponding entries and then add all of them up, so it becomes -4, then x multiplied with 1, that gives you plus x, then y multiplied with 2, that gives you 2y, which is also equal to 0. So from this case we have found a really nice equation, and from this case we have found another nice equation. So from these two equations, hence we can write, so this equation is not in the standard form. So what I mean by standard form is the constant terms on this side of the equation and all the variables on this left side of the equation. So let's try to do that. So if I take this constant term over here, it becomes negative 3, and if I multiply the whole equation with minus 1, then I get x minus 4y is equal to 3. That's coming from this equation. And then from this equation, what I can write is x plus 2y is equal to 4. Now both of these equations are in the standard form. Now I can subtract this equation from this, so I can write it with so these are the signs, and then I subtract them. So then these two cancel each other out. It's plus and it's minus, and this is minus, this is also minus, so we have 4y minus 2y, which is going to be minus 6y, and then we have positive 3 and negative 4, and that gives you negative 1. So from here what we can write is y is equal to 1 over 6. Now we have found the value of y, but we don't know what x is. So I can plug this y value into this equation. So let's call this equation 1. So I can write substituting in equation 1, what we get is we have x minus 4y, so x minus 4, and the y is 1 over 6. You can write 1 over 6, which is equal to 3. Okay. Now if you take this term over to the other side, then you can write x is then going to be 3. This becomes then plus on the other side, and 4 over 6, that can be written as 2 over 3. Therefore the x value is going to be 3 times 3, 9, plus 2 is 11, so it's going to be 11 over 3. So this is the x value, and we found that this is the y value. So we have found a unique x value and unique y value. So what that implies is that for this x value that we have just calculated and the y value, if I take the dot product of this vector with this, it will always produce 0, and the dot product after plugging in the x and y value that we have found, if I take the dot product of this vector with this vector, it will always give you 0. So which means that this vector is orthogonal to this vector and also this vector for the value of x and y that we've just calculated. Now these two values are unique. I mean, there is no other x value or other y value for which this condition would be true. The condition here is essentially that this vector has to be orthogonal to both of these vectors for certain x and y values. These are those specific x and y value for which the first vector will be orthogonal to both the second and third vector that we are given. So I can write the only solution is, so let me write it down, the only solution is x comma y, which is equal to 11 over 3 comma 1 over 6. So this is the only solution. These are the values of x and y for which it satisfies the given condition. See you in the next lecture.